Okay, so we're kind of done with work energy theorem here now. Okay, we're going to be moving on to the last thing, well, second to last thing, okay, in this unit, which is conservation of mechanical energy. Here's the good news about conservation of mechanical energy. I am going to teach you absolutely nothing new. You learned all of this stuff in Science 10, so this should all be familiar, all be a review for you. Okay, like the roller coaster kind of questions, that's what we're looking at here. Okay. So, in a law of conservation of mechanical energy situation, there is no work being done because there's no change in energy. The initial energy and the final energy are equal, right? They're the same. Okay? So there's no energy being lost to any non-conservative forces, okay, or anything like that. It's just EI equals EF. Okay? So the big things we got to remember here about law of conservation of mechanical energy, it says that energy cannot be created and it cannot be destroyed. It can be converted into other forms, it can be transferred, whatever, but it cannot be created or destroyed. Okay? Understand energy obviously can be converted from one form to another, and then be able to use this concept to calculate other variables related to the mechanical energy of an object. So in a roller coaster type question, okay, you could have, I tell you how high the roller coaster is and how fast it's moving at the beginning, and you have to figure out how fast it's moving at some other point along the track, okay, or something along those lines. Now, here's the thing that most people mess up about law of conservation of energy questions. Is energy vector or scalar? It's scalar. Okay, so regardless of which way the object is moving at any point in its path, does that affect how much energy it has? It doesn't. It doesn't matter whether the object is moving up, down, some weird angle. It doesn't matter. If it's moving, it has kinetic energy. Okay, and that's something that people often forget when they're looking at like different types of mechanical energy situations. Okay, in this formula here, this is 1/2 times mass times speed squared, not velocity, speed. Right? It does not matter which way the object is going. Right? Because very often I'll ask people something like this, just because it's kind of funny. I'll say, like, a seagull is flying over top of you. What should you never do when a seagull is flying over you? Look up. Don't look up. Think about it. It'll poo on you. Okay? And usually when you look up, you do this. I've seen it happen. You don't want that. It's gross. Yeah. Person looked up and the poop went right in their mouth. Oh. Really gross. Okay? So, someone says, there's a seagull. Go, okay. Just look straight down. You've seen a seagull before. You know what they look like. All right. So, seagulls flying this way at, let's say, 15 meters per second. And they are, let's say, 20 meters off the ground. And then they poop. Okay? So, let's say that they poop, I don't know, 0.005 kilograms worth of poop. Okay, it's 5 grams. It's probably a big jump, but okay, that's how much. All right, when they do that, does that poop have kinetic energy? Yes, it does. It's moving at the same speed as they are, right? I mean, think Newton's first law, right? You've got something and you're moving and you drop it. Okay, if I'm just walking and I drop something, it's got kinetic energy because it's moving the same speed I am. Okay? Well, the same is true in this situation. But if I give people a question that's like that, they forget. They forget that 15 meters per second is part of the falling object's mechanical energy. Okay? It has kinetic energy. It doesn't have to be falling. Okay? Sure, the bird's flying horizontally. That doesn't make any difference. Whether they were moving horizontally or whether they were moving vertically doesn't make any difference. It's moving at 15 meters per second. It has that much kinetic energy based on that. Okay? Everybody all right with that idea? Okay. All right. So, two kinds of energy, kinetic, potential. We talked about those yesterday, day before yesterday. Okay, the sum of those two kinds of energy is the total mechanical energy. That's also review. We've been talking about that for several days now. So mechanical energy is EK plus EP. Okay, And then this is what we've been doing. This is work energy theorem right here. Okay? Work against any non-conservative forces is EF minus EI. In a law of conservation of energy situation, no work is getting done, so EI equals EF. Right? There's no work being done. Or EF minus EI equals 0. And whichever way you want to look at that. So, if this roller coaster was in the perfect physical world, okay, up here, let's say they have 600 joules worth of potential energy and 100 joules of kinetic energy. When they're down here at their lowest point, let's say this is ground level, how much kinetic energy do they have? 700 joules, okay? Because they'd have no potential and all of their mechanical energy would now be kinetic. All right? Everybody okay with that idea? All right. When they get to this point here, let's say they've got 200 joules of kinetic energy. How much potential do they have? 500. Right? The amount of total mechanical energy is always 700. That doesn't change. Okay? How much of it is kinetic, how much of it is potential is always changing in a law of conservation of energy situation. Okay? All right, questions on that? Hopefully that's somewhat familiar from Science 10. Okay, so in other words, the final mechanical energy is equal to the initial mechanical energy, so consequently the total mechanical energy remains constant along the path between the initial and final points. Okay, it doesn't vary ever. All right. Now, as you guys know, I'm a nerd. If you didn't know that, I'm a nerd. It's okay to admit that. It's always better to admit you have a problem. Okay? Now, this picture here is like the epitome of my nerdness. Okay? Back when I coached track and field, okay, we went to track and field provincials in Edmonton, and this is in the shot put area. And so I'm watching the shot put, and then I watch these guys. And you're probably thinking, like, it's a ramp. Right? They would put the shot put up here on the top of the ramp, and then it would roll down the ramp, and then it would roll along this track. And when it would get to the throwing area, it will have slowed down so much that it just stops when it gets to the throwing area, each and every time. So I'm watching this, and people are just not getting how incredibly cool this is. Because they just see this thing that returns the shot put. They don't realize how much physics went into the design of this thing. Okay? Because this is not like the bowling alley, right? Like the ball return at the bowling alley, you know, you can break your fingers, and little kids are always getting their fingers squished in there because the ball's still moving really fast, and they got that thing to stop it. This uses conservation of energy and work energy theorem to make sure that when the shot put returns to the throwing area, it has no mechanical energy left. Okay? So what they did is they figured out how much friction would be present along the length of this track. Okay? So they knew how much work would be done or how much energy would be lost to friction along that length of track, and then built a ramp that was high enough so that they gave it that exact amount of mechanical energy when they would put the ball on the top. And it worked perfectly every time, as long as you just placed it on the top and let it go. If you give it a little push, then it would go too far. But just placing it on the top of the ramp, okay, got it to the end, coming to a stop each and every time. Okay, now you're probably thinking again, that is pretty nerdy, Coder. It gets worse. I thought it was so cool, I got the whole track team and brought them over. And I'm like, you guys gotta see this! And I'm showing them and I'm explaining it all to them, and I didn't even realize there's like all these other people that are watching the shot put, and they look at me like I am absolutely bonkers. Because I am. But it was a total application of physics. I later found out they actually designed and built this in the engineering faculty at the U of A. Okay? It wasn't just something somebody fabricated and threw together. It was actually designed and built to do exactly that job. Okay? So, real world application of physics. Right there. Okay? If you ever think you can't use any of this stuff, you could build a shot put return device sometime that would work perfectly. All right. So, prime example of, okay, law of conservation of energy, bobsled, okay, or luge or skeleton or any of those things. When they design the tracks for these, they have to really be careful okay, when they're designing the curves. If they make the curves too tight, the bobsledders or losers or whatever, they might be going too fast when they get to those curves. And if they are, what will happen? They not only could flip over, but they could actually leave the corner, right? They might actually fly out of the track. This actually happened in 2010 in Vancouver. Okay? There was an athlete who was actually killed because of this problem. They had warmer weather than they'd anticipated, so they were having trouble keeping the ice there, and so they turned up the refrigeration a little bit, and they made it a lot more slippery than they had intended, and the first person to go down the track went right out. Okay, and they were killed because they were going way too fast when they got to the first tight corner. Okay? So what they ended up having to do was actually move everybody further down. They had to start further down the track. Okay? Why did moving them further down the track fix the problem? Well, if I don't start from up here, but I start from here instead, what have I taken away? I've taken some potential energy away, which means I'll have less kinetic energy when I get to that tight corner, and I won't be going as fast, and as a result, I don't fly out and everybody lives. Okay? But it was kind of a tragedy because they didn't realize just how slippery and how quick that track had gotten as a result of just the conditions there. Okay? All right. Now, the other thing you can see on this diagram here, obviously the amount of mechanical energy is always the same all the way down the track, okay? But how much of it is kinetic and how much of it is potential is always changing, okay? All potential at the top as long as they're not pushing the sled, okay? All kinetic at the bottom. All right. So, I'm going to show you a video of this in a minute. There's a guy that actually did this, okay? He jumped a bike over his name is Evel Knievel. He did a bunch of really crazy things, actually. And he tried to launch himself over the Snake River Canyon. He jumped over the Grand Canyon. He jumped over a bunch of things. Because, well, he was just dumb man. Crazy. Okay. But let's see if we can figure this one out, then I'll show you the video. Okay, so the motorcycle rider is going 38 meters per second on the first side of the cliff. On that side of the canyon. And on that side of the canyon, they are 70 meters above the bottom of the canyon. Okay? We want to figure out how fast they're going when they land on the other side of the canyon when their height is 35 meters instead. Okay? Now we're assuming there's no non-conservative forces. There's no friction or anything. If there's no friction, what do I know about this point and that point? What's the same?
EK and EP.
Right. Well, not EK and EP, but what they add up to, which is mechanical energy, right? So the mechanical energy is the same. How much of it is potential and how much of it is kinetic is going to be different, okay? All right. So those two numbers are going to be equal, all right? So thus begins a law of conservation of energy question, okay? So I'm going to say EI equals EF, okay? So that's mechanical energy. I'm going to expand that out to say that means initial kinetic plus initial potential equals final kinetic plus final potential. Everybody okay with that? Do I have formulas that calculate kinetic and potential energy? Yes. Okay, so I'm going to expand that out further. 1/2 mvi squared plus mghi equals 1/2 mvf squared plus mghf. Okay? Are any of these energy forms zero in this question? Okay? I have kinetic energy here at the beginning. I have potential energy here at the beginning. Okay? I'm not at the bottom, so I would definitely have kinetic. Okay? And I'm not at the bottom, so I definitely have potential. Right? Everybody okay with that? So I've got all of these, none of them are zero, but what's in every single one of these terms? Mass. What can I do with it then? Cancel it. Yeah, which is good because I don't think they ever told me, they didn't, how heavy the bike is. Right? Since it's in every term, I can cancel it off. Okay, so I've got 1/2 vi squared plus ghi equals 1/2 vf squared plus ghf. I'm looking for this, VF. What do we have to move now? Right, subtract GHF over to the other side. All right, so I'm going to have 1/2 VI squared plus GHI minus GHF equals 1/2 VF squared. Okay, what do I move now? 1/2. Okay, and then what? Square root. Okay, so now I can plug in my numbers. Okay, so we're going to have 1/2 times 38 squared, okay, plus 9.81 times 70, initial height, minus 9.81 times 35, divided by 1/2. All right, can this get a little bit crazy when you're entering it into your calculator? It can. So you can do it all in one step and use tons and tons of brackets, or you can do it one step at a time and do it that way. It doesn't matter to me, whichever way makes more sense to you. Okay, so 0.5 times 38 squared, okay, plus 9.81 times 70, minus 9.81 times 35, divided by 1/2, square root that. All right, so when they hit the ground on the other side, they'll be moving at 46.2 meters per second. Is that pretty fast? Yeah. It is pretty fast. It's 166 kilometers an hour. I don't know if I'd want to try to land a dirt bike at 166 kilometers an hour. It'd be pretty tough, I would think, to keep that. All right, is that making sense, everybody? Okay, I'm going to show you the video. Okay, so we just completed that one there. Okay, very typical type of law of conservation of energy question. Okay, so I want you guys to try this one. This would be very typical of one you would have done in Science 10. Okay, so you got a frictionless roller coaster with a mass of 800 kilograms. At one point on its journey, it has a speed of 4 meters per second and is 35 meters above the ground. Later, its speed is measured to be 20 meters per second. Okay, calculate its total initial mechanical energy and then what its gravitational potential energy would be in the second instance. And for part C, how high above ground is it? Okay, give you a few minutes on that one. All right, so to calculate mechanical energy, all we do is take the kinetic and add it to the potential. All right, so that's going to be 1/2 times 800 times 4 squared plus 800 times 9.81 times 35 meters. All right, so that'll get us the initial mechanical energy. So 0.5 times 800 times 16 plus 800 times 9.81 times 35. All right, so there's our initial mechanical energy, 281,080 joules. Okay. All right, so there's our initial mechanical energy. Now, it says that later, it's moving at a speed of 20 meters per second. So if I want to find its gravitational potential energy in the second instance, and I don't have the height, how do I do that? Pardon me? Well, I don't have HF yet. Let's say I don't have HF, but I'm looking for the gravitational potential energy. You're right, I could just solve for HF and then go back and do this, but what I'm trying to show here is this idea. What do I know about this number?
You subtract kinetic.
Yeah. That's the mechanical energy everywhere along the path of the roller coaster, because the mechanical energy is conserved, right? So anywhere along the track, it has that much mechanical energy. So if I take that number and I subtract the kinetic energy that it would have when it's moving at 20 meters per second, that should leave me with the potential energy at that point, okay? But I have to recognize two things. first off, that this is how you calculate mechanical energy, and that number is not going to change anywhere along the track. Right? So I take my 281,080 joules, and I subtract 1/2 times 800 times 20 squared, and that'll give me my new potential energy. So minus 0.5 times 800 times 20 squared. All right, so I have 121,080 joules worth of potential energy left. Now that I know that, can I calculate the height? Right? So this equals EP, which equals m times g times h. Okay, so if I want to find h, I'm just going to go EP divided by mg, right? I'm just going to move the m and the g over. So that'll be 121,080 joules divided by 800 times 9.81. All right, so it's still 15.4 meters above the ground. Okay, is that making some sense? Ringing the bell? Okay, I'm going to make this way bigger. All right, I want you guys to try number 2 for right now. Okay, so we're going to have a look at number 3 maybe today. We might get to it. Okay, but just try number 2 for now. I'll give you a couple minutes on that one. Okay, let's have a look at this one. So they tell us first off the mass. It's 55 kilograms. Okay, they tell us it is 225 meters above the ground initially, and that it's moving at 36 meters per second. Okay. We want to calculate its final speed or final velocity, they're saying, because it's down, okay, and that wouldn't change because it's just falling, okay, when it's at a final height of 115 meters. All right, so we're just looking for VF here. Is this exactly the same calculation we just did? It is. Right, looking for VF. It's exactly the same calculation as the bike over the canyon. Okay, so we're going to have EI equals EF. Okay, that's going to be EK initial plus EP initial equals EK final plus EP final. Okay, none of those are 0. Okay, each of them has an actual number value. All right, so now we can plug in our formulas. That's going to be 1/2 MVI squared. Okay, plus MGHI equals 1/2 MVF squared plus MGHF. Okay, M's in every term, so I can cancel it unless you don't want to. Then you could put in 220 or 55 kilograms for each one of those if you wanted to. It's entirely up to you. Okay, I try to use as few numbers as possible because there's less chance for me to screw something up. Okay, but it's entirely up to you. Right? I'm trying to find VF, so I want to subtract GHF over to this side. So I'll have 1/2 of VI squared plus GHI minus GHF equals 1/2 VF squared. Okay, then I'm going to divide both sides by 1/2 and square root. That'll leave me with VF. Okay, then I can plug in my numbers. So 1/2 times 36 squared plus 9.81 times 225 minus 9.81 times 115 divided by 1/2. Okay, and that should give me my final speed at that point. So this is what it looks like, guys, if you're doing it all in one step. So if you're using tons and tons of brackets. Okay, so we're going to be moving at that point at 58.8 meters per second.
So like on a unit test, would we have to like show like EK equals EF and then draw it out like the equation like how you do it?
Well, a question like that would be probably worth about 5 or 6 marks. I would show at least some of the intermediate steps just in case you had an entry error and didn't end up with the right answer. Because if all you show me is EI equals EF, VF equals 58.8, right, and 58.8 isn't the right answer, then there's not much I can give you other than 1 for EI equals EF. Right, so make sure you show at least some of the intermediate steps. You don't necessarily have to show them all, but. So if you showed EI equals EF and then maybe like one of these somewhere along the way, just so I could kind of follow what you were doing, that'd be good. Because I know it's a lot of writing, it takes time. All right, now number 3, guys, is about as involved as a law of conservation of energy question could get. It's about the Human Cannonball. And this one incorporates some of your knowledge of projectile motion as well as your law of conservation of energy stuff. Okay, so they're shot out at a speed of 21 meters per second at an angle of 20 degrees above the horizontal from a platform that is 15 meters above the ground. Okay, the acrobat has a mass of 56 kilograms. What's his gravitational potential energy relative to the ground when he is at his highest point in his flight? Now, when he's at his highest point in his flight, does he still have kinetic energy? This is what I was talking about at the beginning of class. Is he moving at his highest point? Yes. Then he does have kinetic energy at his highest point. Which way is he moving at his highest point? Straight, horizontally. Remember, at his highest point is when his vertical velocity will be. According to projectile motion, at your highest point, your vertical velocity is 0. So his only velocity is the horizontal component of his initial projected velocity. That's the thing most people forget on this question, okay? Is that there's that element of projectile motion involved here. We used to put a question like this back when we had IB here. We had Physics 20 IB. This used to be a final exam question, okay? Because we would see how many people remembered their projectile motion and conservation of energy all in the same. Okay, we're going to look at that one. Start a class on Monday. Okay. So if you guys can get your desks wiped down, please, that would be awesome.